because we have already. So the idea is this. See, understand this. Now I'm sure you all will be able to follow all this. This is not tough and all, but this is more conceptual. Suppose you have a conductor like this, okay? So when you're saying that a conductor or a body is positively charged or a body is negatively charged, it just technically means addition or removal of electrons. If this body is positively charged, what it means that some electrons you have removed from the body. So everything in universe is actually neutral, but once you remove these electrons, then this will be having excess of positive charge. Correct? No problem. So that is how we say that this body is positively charged. Same way, if you add electron to the body, we say that the body is negatively charged. We cannot add or remove protons or nucleus. All right, because adding or removing nucleus takes up a lot of energy, which is impossible for us to do. All right, it will be possible, but that is a matter of discussion when we talk about modern physics, not here. So every time you charge or remove charge from a body, whether it is positive or negative, it technically means that you have added electron or you have removed electron. Is that part clear to everyone? Yes. That is why quantization of charge, we have told that Q is equal to n times of E. Yes, when we were discussing quantization. Next thing is that if you imagine a conductor like this, and let us say you deposit some charge over here, you put some charge over here. So what will happen is that all these charges will, all these electrons, all these negative charges will repel one another, and they're free to move inside a conductor. Did you understand? So a conductor has something called as free electrons. If you have seen the structure of a metal, and if you remember atomic structure, you know that the outermost shell, their electrons are loosely bound and they can travel, they can move around, right? So they can move around in the lattice itself, in the same body, but they're loosely bound, right? So these are free to move and they are called as free electrons. So all these electrons will repel one another and they will occupy the outer surface. They will always occupy the outer surface. Did you understand this? So there will be no charges inside this, in the bulk, in the volume. The charges for always for metal or for conductor, the same thing is going to happen. The charges will always and always be outside. This is also called as a shielding effect. That's why when there is a thunderstorm or something, people say that you should stay inside your car. Must have heard about it, right? Correct? Must have heard about it or read about it. Or there is a famous thing called as Faraday's cage, wherein there is this guy who is sitting inside a cage, and outside there is all this lightning. Must have seen a Nikola Tesla picture wherein he sits and reads a book inside a cage, and outside there is, lightning going on. So very high voltage. So just because this is a metal, all the charges will appear on the surface, and inside it is going to be zero. All right. Of course, we'll add on to this concept, but this is what happens. Uh, Same thing happens when you have a positive charge. So suppose you have positive charge, and how you can imagine is if you have positive charge in the bulk of a metal, all the negative charges which are over here, all these charges will get attracted and they will come towards the center so that they can cancel off this. And you will see a net positive charge on the outer surface. So on the metal, the charges always appear on the surface. Is this point clear? Or on a conductor, the charges always appear where? On the surface. Is this point clear, everyone? Yes? Anyone has got any doubt? No problem. Also, if you talk about a conductor like this, and if the charges are appearing at the center, on the surface, suppose like this. So now this charge is distributed over the area, correct? The charge distributed over unit area is called as charge density, and we write it with sigma. We write it with sigma. We say that this is a charge density, no problem. Now, what will happen is that this charge density is inversely proportional to the local radius of curvature. What does that mean? It means that if you look at this point, if I talk about this small segment, this will be a part of this circle, whose radius is r. And if I talk about this segment, this will be a part of a larger circle whose radius is, let us say, r1. Clearly, I can see r1 is greater than r. So charge density will be more over here than over here, which means if if the things are pointed, then the charges will be more. That is why you see the lightning conductors like this on the top of the building. Have you seen something like this, right? Or if you have seen welding, so welding machines, you'll have this type of a protruding, a pen type of structure where the tip is where you can see the lightning coming out. Have you seen that torch, the welding machine? I mean, these guys who wear something like a mask and they are welding, no, there's so much of light coming out. Have you seen that? So in welding also the same thing happens. The basically there is so much of positive charge over here that the air molecule gets ionized, and the electrons from this guy, all these air molecules, they start bombarding on this, and because all these charges are attracted, it just melts this metal. Did you get it? So which means the sharper the object, the more the charge will be accumulated. So if I tell you that, okay, tell me for this and this one, if I put charge, equal amount of charge, which part is going to have, this is part A and this is part B, which part is going to have a larger charge density? Definitely part B. Did you understand? The sharper the edge, the more the charge. Did you understand this, all of you? Just some additional things. Cool. Now also we know, if I have got a charge q over here, plus q, and over here another plus q charge. Okay. So if I think, where should I keep a charge, a third charge, such that the net force on this third charge is exactly equal to 0? Okay. So of course, I have to keep which charge? If I keep plus q, this charge is going to repel it in this direction, and this charge is going to repel it in this direction. Yes or no? Yes, correct. So if I call this as q1, if I call this as q2, very, very common question. Where should I keep this? So you say that from the first charge, let us say it is at a distance of x. The total distance between the two charges is r. So this distance will be what? R minus x. All right. So now this force, this is F1, this is F2. F1 will be equal to k q1 small q upon x square. Similarly, F2 will be equal to k q2 small q upon r minus x squared. Yes. The point where this is going to be equal is going to be when F1 is equal to F2. Correct? No? No problem? Did you understand this? All right. Now, when you solve this k q1 q, this small q k and all this will get cancelled out, and you'll get a quadratic in x. Correct? Yes. And by solving that quadratic, you'll get 2 points, wherein this will be equal to 0. One will be negative, one will be positive. The positive one you can take. Did you understand? Yes, a very, very common question. It's been asked so many times in your this board exam. All right. So something you should practice. I'll also give you a shortcut formula for that one. Don't worry about it. I'll also give you a shortcut formula, but that's how it is. All right. Okay. So we are discussed. Huh.
So can you go to the previous slide?
Previous slide.
So the diagram you drew before this.
This one.
So
this.
did you write R1 greater than R?
Yes, this was R. And this, let us say this one is R1. Okay. This is a part of a larger circle. No? Local radius of curvature means that if you draw a circle passing through that segment, the radius of that circle is called as the local radius of curvature. Okay.
Right.
So sigma, that is charge density, is inversely proportional to R. So larger the R, lesser the sigma.
Yeah.
So if R1 is greater than small r, That means over here the charge density sigma will be greater,
Yes, sir.
and charge density was nothing but total charge which is appearing on this area, which means the number
Yes, sir.
of charges which will appear over here will be larger as compared to the number of charges. So sharper edges will have more charge density. Got it?
Yes, sir, but how is that concept relevant in the second part, like F1 equals F2?
It is not. It is not.
Okay,
It is
okay.
not it. It is not.
Yes, okay.
It has nothing to do with this thing. This was the I was just telling you that like you need to remember understand that basically.
Oh, okay, okay. Yes, sir.
Is it okay? So in the last class, I think we have already completed Coulomb's law, the vector form of Coulomb's law. Permittivity did we do last class? We have done permittivity, right?
Yes, sir.
Okay.
So
Which
we
means now
stopped
we'll
at
talk.
superposition.
We stopped at superposition. Okay. So now we'll talk about the characteristic of Coulomb's law and its basic like where it is valid, where it is not valid. All right, and then we come to the electric field concept. Is this part clear? That there is one this very popular question which I thought that you should understand, and they will ask you many a times that where is the net force zero. They can also have this as minus and this as plus. Depends. Accordingly, you can also judge what type of charge you should have over here. The borderline is that the net force on this charge has to be equal to zero. Now let's move to the characteristic of Coulomb's law. So Coulomb's law is valid only for point charges. Only for point charges. Correct. Now this looks good as far as the theory part is concerned, but you must ask questions why. Why it is only valid for point charges. So if you see Coulomb's law, the distance between the two charges was center to center, that is from point to point, correct? But something will happen actually. And also that also talks about permittivity. So imagine we have a large object like a sphere. We have another large object like a sphere, and we have positive charge over here. Their center to center distance is, let us say, r. And if I have got another sphere over here positively charged, let's say the charge over here is q1, the charge over here is q2. Now what will happen is, because of the presence of this charge, the positive charges will get repelled, which means what will happen? You will have positive charge center shift over here, correct? And similar thing is going to happen over here as well. Yes or no? Positive charges will shift over here, correct? All right. Yes. So if you see the actual distance is r, but now the the charges have shifted, so the center of the charge will shift. So the center of the charge will shift. And now this is going to be the center to center distance. The center means what? Center of the charge. Did you understand this? Not the center of the sphere. That's why we take point charges, because a point has got 0 dimensions, right? Correct, no? So now since these charges have shifted towards one side, what has happened? R effective is greater than R. That means Coulombic force, when you write the formula KQ1 Q2 upon R square, will not give you the correct result, because this force is less. This force is less. Correct, no? Than the actual force. So you calculate the actual value. Sorry, this force is more than the actual value, because R effective actual F actual will be lesser than F Coulombic. It is going to measure more, no? Because R it is measuring less. Did you understand? All of you are understanding this? That is why we say that it is valid only for point charges. Coming to that point, actually what happens when a point charge approaches a body having charge? Did you all understand this point, that why it is valid only for point charges? If you think about opposite charges, then it is going to give you more value. Basically what will happen is, see, if this is negative charge, if this is negative charge and this is positive, then you see what will happen. Then if this was positive, then positive charges will get attracted like this, and negative charges will move like this because they will get attracted towards the positive charge. So again the charge density shifts, and the actual radius or actual distance of the center of the positive charge will become lesser. Did you understand? Because both are coming closer, no? Right? And if both coming close, then actual force that you are going to measure will be larger than the Coulombic force. So Coulomb force will not give you the correct value. And it's a law, right? Coulomb's law. So it has to be correct. That's why we put the condition that it has to be applicable only from point to point. Got it? Also, in case of permittivity, we had seen that the force had become less, right? Correct? The force had actually decreased when we were talking about two charges and there was a medium, and that medium was having some kind of a effect. And but if I want to know what kind of a effect, then like what do we do? If I want to know that what type of effect is that, what effect the medium has on the body, that's what we want to understand. I'm taking a little deeper, probably beyond NCRT, but it's important for you to know that in terms of concept so that nobody can trap you in terms of concept. So we know that the force decreases by epsilon r. We know that the force decreases by epsilon r, yes or no? Yes, correct. We know that when we place it inside a medium, the net force decreases. But actually, the force that the first charge up gives on the second charge and the second charge applies on the first charge does not vary. The Coulomb force actually changes because Coulomb force gives you the net force. So for understanding that, we need to see what happens when a body is kept in a medium. Imagine you have a sphere. This is a metallic sphere. And if it is a metallic sphere, just now I have told you that all the charges are going to appear on the surface. Now imagine you take a plus q charge and you bring it close to this sphere. What will happen? This plus q charge will repel these positive charges, and these positive charges will be repelled. And what will happen after some time? You will see a charge redistribution. You will see a charge redistribution. Did you understand? This is called as induction. This is called as what? Induction. So since this topic has been taught in your school, you must have come across two different terms. One will be charge induction, another would be polarization. Have you heard about this term, polarization? Right? So when we talk about a charge separation, in case of when you bring this charge, what will happen? This positive charge is going to repel this, guys, right? So because of that, there is a charge redistribution over here, which we are calling it as induction. This is induction. Now, if you think about a same plus q charge, which is brought near a non-conductor, what happens in case of a non-conductor? In case of a non-conductor, see what happens. In case of a non-conductor, you have got this nucleus, and then there is an electron cloud like this. There is an electron cloud like this, all right? The moment this plus charge comes, this electron cloud gets attracted towards this guy. So the electron cloud starts getting distorted. Are you all following this? So this is how the electron cloud is going to look like, which means now there is a net negative charge over here and the positive charge shifts slightly like this. No problem. This is what happens in case of a medium, and which is a what you say, a non-conducting medium. And this is called as polarization. This is called as what? Polarization. Amartya, Rishi, Elvin. Where is Pranav? What happened?
I saw some network issues, so he got disconnected. He'll join again. Sir, also, charging due to induction is not there for us. It's deleted.
Oh, okay.
Yeah.
Charging due to induction is not there. But anyways, you will require
Yes,
or
sir.
this concept. You'll require this concept. Okay. Other guys are there? Amartya, Rishi, Elvin, are you people there?
Yes.
The internet issues.
Yes, over here.
Okay. So did you understand this? this idea of polarization and this. So see what happens is, if you take a non-conductor and you place a non-conductor like this, polarization will happen. So negative charge plus positive charge like this will get arranged. Negative positive like this will get arranged. Negative positive like this will get arranged. And what will happen? They will have a force of attraction like this. So net force, if you see, gets decreased, right? Net force is getting decreased. If there was a positive charge over here, plus Q charge, here also, this plus Q charge would have applied a force like this, and the medium is opposing it. Can you see that? Because of the presence of this medium, there is now force due to medium. This is force due to plus Q. Did you understand this, guys? So overall, when you see the net force, it decreases. And the ability of a medium to get itself polarized like this is called as permittivity. Now, did you understand the actual meaning of permittivity? Understood?
Yes, sir.
Amartya, Rishi, you guys understood what happened?
Yes, sir.
That we say no, that the force decreases, but why does the force decrease? If somebody wants to understand that, like what happens when you place, we have told no that if you put it inside water, it will decrease, right? The question is, why will it decrease? The reason is this kind of a polarization. The reason is this type of polarization. So what happens now when you see the force on this guy, the net force has decreased because the medium is also applying a force in opposite direction. So that is why the net force decreases. Got this? Okay. Okay, no? So coming back to the idea characteristic for Coulomb's law. So we understood that it is only valid for point charges, and we know why. Point number two is it is only valid for charges. At least one charge has to be at rest. At least one charge has to be at rest. This is the actual thing, but you might go across that, okay, both the charges have to be at rest. It is valid only for charges at rest. The real thing is that at least one charge has to be at rest. What will happen if the charge starts moving? Suppose if this starts moving with velocity v1, if the charge starts moving with velocity v2. Now, if you remember your 10th standard, you have studied, no, that a current carrying conductor behaves as a magnet. Ostrich experiment. You have heard about that Ostrich experiment, all of you? That a current carrying wire behaves as a magnet. If a charge starts moving, it produces something called as magnetic field. Did you understand? So if a charge starts moving, it produces magnetic field. So this will produce a magnetic field, and this will also produce a magnetic field. Their magnetic field will start interacting, and the net force will now be given by Coulombic force plus magnetic force. Did you understand this, guys? Now, since we are studying about Coulomb's law, we cannot have any idea about the magnetic force, right? That is why we say that Coulomb's law only measures the force between two static charges. Did you get this? Amartya,
Yes.
Rishi, Elvin.
Could you repeat it? Your voice is breaking a bit.
Okay. What I'm saying is that if when you talk about the uh, validity of Coulomb's law, it is only applicable for charges at rest. But the real thing is that if one charge is moving, doesn't matter. All right. But if both the charges starts moving, a moving charge produces a magnetic field around it. Now, if both the charges are moving, this guy will start creating a magnetic field, and this guy will also start creating a magnetic field. These magnetic field will interact with one another, and then what you measure cannot be deduced by Coulomb's law. Then there will be an additional force, which is magnetic force. Did you understand? Why I told that even if one charge is moving, the other charge is at rest is still valid, because the magnetic field affects only the charges which are in motion. Magnetic field cannot apply a force on a charge which is at rest. If you remember the formula, the magnetic force was equal to VLB, V into L cross B. We'll get that into more detail, but it needs to have velocity. Correct? Did you understand? Okay. We also have to understand the nature of these forces. So see, similar thing will only attract or repel similar thing. Basically, electrostatic forces are going to attract or repel electrostatic forces. Electric field is going to affect electric field. Magnetic field is only going to affect the magnetic field. They won't affect one another. Did you understand? They never affect one another. For example, uh, like signal. For example, you have got audio signal and video signal. Suppose the light in your room is less, so the video signal will be having a disturbance, but the audio signal will still be okay. Correct? There will be no interference. Are you getting it? Because light is a different wave and sound is a different wave. Did you understand this? So sound can be disturbed only by sound, another sound wave. If somebody starts knocking, if somebody starts shouting, then you'll have a problem. But otherwise, it is all okay. So light can be affected by light. Similarly, sound can be affected by sound. In the same way, electric field will get affected only if there is a charge, which is creating an electric field. Got it? And magnetic field will be affected only by magnetic field. Got it? So, although in NCRT it writes that both the charges should be stationary, even if one is moving, doesn't matter. Still, Coulomb's law is valid. But if both starts moving, then it is not valid. Then there will be an additional force, which we call it as magnetic force. Clear with this?
Yes, sir.
So it is applicable and it is valid for point charges which are at rest. It obeys, of course, the inverse square law. It is a long range force, which means, of course, the value of this force will become lesser and lesser. You know that if you go 2 times, the force becomes 4 times lesser. If you go 3 times, the force becomes 9 times lesser. If you go 5 times away from one another, the force becomes 25 times lesser, and so on. Which means if you look at the graph, the force will decrease exponentially like this. The graph will be like 1 by r square or 1 by x square, like this. Got it? So it keeps on decreasing because it follows the inverse square law. All that I am talking about, everything is there in your notes. Okay, so don't worry about noting it down or anything. I've given you notes already, right? Everything is written there. Just try understanding things. Okay. Now, if you talk about the validity of Coulomb's law, if the two charges are at such close distances of 10 to the power minus 15 meters, which is 1 Fermi, which is nothing but a nuclear radius, then this force is not applicable, because then what is applicable is the strongest force of nature, which is the nuclear force or strong nuclear force. Got it? Then what is applicable is the strong nuclear force. So that time this force of repulsion does not act. The nuclear force is an attractive force. It doesn't depend upon the charge also. And we know inside the nucleus there are nucleons like protons and neutrons. Neutrons are neutral. Still, they are attracted to one another. But details about it we'll study in the chapter called as nuclear physics, not now. Only we need to understand that if the charges enter inside the nucleus, there is another force which binds them inside the nucleus, and that force is called as nuclear force. So Coulomb's law has no validity over there. Understood? Okay. It's a central force, which means it always acts along the line joining the center of the two bodies. And when we say center, we mean center of the charges. Cool. Coulomb's force depends upon the medium within which the charges are placed. We have already discussed that in great detail. And it obeys Newton's third law of motion, which means there is like equal and opposite. It has an action-reaction pair. Okay. And Coulomb force is not affected by the presence of other charges bodies placed at it. Because if you look at this charge Q1, the force that it applies on Q2, if it is at a distance of R1, will be equal to K Q1 Q2 upon R1. If there is another charge Q3, which is at a distance of R3, this will apply, Q3 will apply its individual force, no? K Q2 Q3 upon R3 ka square. So this force has nothing to do with this force. Did you understand this? The net force on this body is, yes, the net force is that vector sum of these forces, but this force has nothing to do with this force. they keep on applying their own force as if nothing else is there. So it is not affected by any other charges. Got it? Okay. So these are the basic characteristic or limitations of what do you say, Coulomb's law or Coulomb's force. Got it? No problem. No problem till this point. Now we start after the break. 10 minutes break. We'll start with the concept and idea of electric field and electric field intensity. So we'll see electric field intensity, which is very similar. Then we talk about the electric lines of force. Again, the properties of electric lines of force is very, very important. It's a representation and all. And then we go to dipole. All right. In the meantime, Lakshita, if you can just call up Pranav and
Yes.
Amartya, anyways, you'll be sharing the recording with Pranav, right? So what he has
Yes,
missed,
sir.
he can quickly go through, and you can tell him that if he wants, he can just use his mobile data to connect and just come for the class. All right? Don't want him to miss
Yes.
on the important topic. So I'll see you in 10 minutes. All right?
Yes, sir.